Static systems experience two types of interactions: forces and torques. Sometimes we call them moments, but we'll get to that later. Forces are actions of one object on another that tend to cause linear motion, where torques or moments are things that tend to cause rotation. That being said, a force can cause a torque that leads to rotation, but that's a topic for a different discussion. Right now, what we want to talk about is the fact that forces are vector quantities, are vector quantities. And what that means is that we care about not only how big they are, but also in which direction they act. The same force acting in two different directions can lead to dramatically different results. And so we're going to want to know not only how big something is or its magnitude, but also what direction the force acts in, its direction. And in general, we're going to use two different methods to communicate which way something points, and we're going to need you to be comfortable with both of them. So one way of communicating the direction is by using an angle. So we have some known reference angle or known reference direction, and we measure the direction of the force relative to that. So for example, we could have a force that comes up like so, that we call F with a little line over it to denote that it's a vector. And we could say that it lives at 30 degrees from the horizontal. The other way that we can communicate direction is by using a unit vector. A unit vector, which is a special vector that has a magnitude of 1. And so while we have the same vector f that we started with before, a unit vector is a little baby vector that points in the same direction. We usually give it a little caret like that. So u hat f is a unit vector that points in the direction of f, and it could be something like 0.87 I hat plus 0.5 j hat. These are the same vector, and we can describe their directions in two different ways, either 30 degrees or using this unit vector. And if we took the magnitude of UF by doing the sum of the squares, right? So we do 0.87 squared plus 0.5 squared, square root that, we would get 1, or at least close to 1 within rounding errors. We're going to write force vectors using 3 different notations, and you should get comfortable using all 3. And not only that, you should get comfortable converting a force expressed in one form to another. The reason for this is that in different circumstances, each of these forms is going to be the most convenient for solving a problem. So let's go ahead and start with the first form, which is the magnitude and angle form. Magnitude and angle form. And this would be something like writing that our force is equal to 100 newtons at an angle of 30 degrees. We typically measure the angle relative to the positive x-axis. The positive x-axis. So, by the way, this is the same vector we were looking at just a moment ago. It looks like 100 newtons long, and it does that at an angle of 30 degrees if this is the x direction. The next form that we will often use is called the magnitude direction sense form. Magnitude direction and sense form. Vectors written in this form would look like this: 100 newtons multiplied by the unit vector 0.87 I hat plus 0.5 j hat. So what we have here is the magnitude of our force multiplied by a unit vector that specifies its direction. And this is, again, the same vector we've been talking about. A thing that looks like this is 100 newtons long and has a unit vector UF that points in the same direction as it. And the only thing that we need to clarify here is what sense means. What's sense? Sense is whether something is moving in the positive or the negative direction. So for example, I could come up with a second vector that we call F2 and say that it is equal to the negative of F. In other words, it is minus 100 newtons multiplied by that UF. And what you would have is if our original vector pointed up like this, right? This was our F. F2 would be the same size vector pointing in the other direction just by multiplying it by a negative sign. And so we would say that this vector has a negative sense in the UF direction. The third way that we can represent a force vector is in Cartesian component form. Cartesian component form. And essentially what we've done here is we've distributed. So instead of writing f as 100 times a unit vector, we would have f is 87 I hat plus 50 j hat, and we tend to factor out the newtons and put it outside once so we don't have to write it 2 times. And essentially, again, this is the same vector. We have a thing like this, and now what we're saying is that it is 87 newtons in this x direction, and it is 50 newtons in this y direction. And we can now represent the same vector using that notation. So really, magnitude, direction, and sense and Cartesian component are the same thing. It's just whether or not we factor out or distribute the magnitude. We can use trigonometry to convert from one form to the other using things like sines and cosines, or cosines and tangents and things like that, and you'll get lots of practice of it. The big thing that you want to be careful of is messing with things that aren't in the first quadrant. If you get a vector that looks like this, and you're looking, say, at this angle here, that's a negative angle. And the result of that is that things can get funky in the sines and cosines and other trig functions, so watch out as you're practicing.